Alright, y'all, to finish up our little expedition into graphing, we're going to finish off with the last two trig functions, which are what and what?
Cosecant and secant.
Cosecant and secant. Those are reciprocal functions, and the reciprocals are what and what?
1 over.
Cosecant is 1 over sine, and secant is 1 over cosine.
Yes. So before I can graph, let's go ahead and start with cosecant first. I'm going to go ahead and sketch the graph of sine. So sine, there was some dots here. So remind me what that looks like.
Sine is a wave that goes through the origin.
Right. It goes up, starting at the origin, goes down, and comes back up in a nice, very smooth, non-abrupt fashion. Well, let's do one more. One more repetition like that. Alright, where does it hit the x-axis?
On multiples of pi.
Yeah, multiples of pi. So there's 0. The top of the hill is pi over 2. X-axis of pi. The little valley occurs at
3 pi over 2.
3 pi over 2, and it finishes
2
off
pi.
with 2 pi. Yes, that's our classic fellow there. Graph of plain old sine of x. Is everything here just negative? Negative pi over 2. Negative pi, negative 3 pi over 2, and negative 2 pi. Yes?
Yep.
Mm-hmm.
So, here in green is the graph of sine of x. Now, as Jordan rightly noted, cosecant of x is 1 divided by sine of x, yes?
Yeah.
And here in green, sine of x are these vertical values, right? So to get the vertical values, the y-coordinates, for cosecant, all I've got to do is I just need to look at this graph in green, pick out a point, look at that y-coordinate, and then divide 1 by it. So, first let's start off like we did for a cotangent and tangent just a minute ago. When is cosecant undefined?
When sine of x is 0.
Yes. And remind me, sine of x equals 0 at multiples of?
Pi.
Yes. Multiples of pi. And so now we got a situation where whenever x is a multiple of pi, we get non-zero divided by 0.
A 0.
So we have, graphically, what kind of objects?
Asymptote.
Yes, vertical asymptotes. So here in green are my vertical asymptotes and multiples of pi. Again, don't forget to include 0. 0 is technically a multiple of pi. 0, pi, and negative pi. Let's do one more. You'll see why in a second. Yeah, let's do another one. Like so. So I know for a fact that cosecant is undefined at 0 pi, 2 pi, negative 2 pi, and so forth. Now let's look at the values where it's defined. Okay, let's look at this graphically. What is the y value of sine of x when x is pi over 2?
1.
Right. So sine has a maximum value, the sine wave has a max value of positive 1. It never extends beyond that upper bound. Likewise, what's the lower bound for sine?
-1.
-1, right. That is the minimum value. It's the smallest value that sine of anything can ever be. But something interesting happens. Let's take the maximum value of sine, 1, and say 1 divided by it. What is 1 divided by the max value?
1.
Right.
Still 1.
That's 1. So 1 point on the graph of cosecant is pi over 2, 1.
Uh-huh.
Now, what are the units over here? If I go from pi over 2 to pi, so now again, I'm just doing it for tangent and cotangent. I want to analyze the interior behavior of this region. What is it doing from pi over 2 to pi? So, pi over 2 to pi, the number line is moving from the left. From the left is a counterclockwise rotation on the unit circle. So when I go from pi over 2 to pi, but let's say I stop just short of pi, at some point just right there. What are the signs of my x and y coordinates?
So since sine of x, well, x is getting going negative,
Yeah, in quadrant 2.
and y is getting
Positive.
smaller, but still positive.
Smaller but still positive.
Yeah.
And remind me, sine of an angle is which coordinate? The x coordinate or the y coordinate?
The y coordinate,
Yes. So the y coordinate is, like Jordan said,
positive,
positive. 1 divided by a positive quantity is
positive.
positive. So as I'm approaching pi from pi over 2, I'm in black here, I'm up here. Alright? So it goes like that. So we're just looking at the y coordinates on the unit circle. We don't care about the x coordinate for cosecant. So now, similar argument, when I go from pi over 2 to 0 on the number line, again moving from the right is what kind of rotation on the unit circle?
Clockwise.
Yes, clockwise. So pi over 2 to 0, but let's say I stop just short of it. Again, I don't want to be undefined. I don't want 1 over 0. If I'm at a point right here, my y coordinate is what? Positive or negative?
Positive.
Positive. So I'm up here again. So I get this nice upward facing U. It's a happy U. It's a happy tree. All right. So for this little segment, I got a nice U with a minimum value that was the max value of sine. Now, let's look at what happens in this region here. So again, start at the bottom of the hill this time, bottom of the valley. If I say 1 divided by this y coordinate for sine, 1 divided by negative 1, that gives me
Negative 1.
negative 1, yes. Now, if I go from negative pi over 2 to 0, so this time from here to here, but I stop just short, my y coordinate is what? Positive or negative?
Negative.
It's negative. So 1 divided by some negative quantity gives me negative 1. Sorry, not negative 1, but just some very, very negative number. Now likewise, if I go from negative pi over 2 to negative pi, I'm going from here, where?
To the left.
To the left. Yeah, just a little bit clockwise, so there to there. But I stop just short, and I don't want to be undefined. I'm going to have a y coordinate here that's positive or negative.
Negative.
Negative. Quadrant 3, negative. So, positive 1 divided by some negative value gives me some very, very negative value here. So, I have a downward facing U. It's an unhappy U. Now, as you
those lines, they never go past the vertical asymptotes.
No. Because when you're at the asymptotes, that's going to make sine 0, and then you're going to have 1 divided by 0, and give you an undefined situation.
Okay.
Okay. And you can verify this for yourself. This pattern is going to repeat. You go from a sad U to a happy U. Then it goes sad. Then it goes happy again.
That's not sad.
And yeah,
Happy is okay, but that's not sad.
I think it's sad. Anyway, to each his own. What is the period of this graph?
Pi.
No.
Would it be 2 pi?
It'll be 2 pi. Again, we're looking for the amount on the the x-axis, that corresponds to a full cycle. A full cycle in this case is when you go from happy to sad.
Oh.
Happy to sad, happy to sad, and that's the length of 2 pi. 2 pi, 2 pi. So yeah, it has the same period. So here's the takeaway. It has the same period as sine. Sine of x, period of 2 pi. But in this case, it's not as nice, not as easy to pick out because the graph isn't as nice. Yeah, it just starts unhappy and then abruptly just goes sad. Okay, next, y'all, is a final graph, the graph of
Secant.
secant, yes. So I'm going to do the same sort of thing. What is the function that I'm going to compare secant to?
Cosine.
Yeah, this time it's going to be cosine. So say y equals cosine in green. And let's start afresh. So, new vertical, new horizontal. Let's see. All right, what does the graph of cosine look like?
Same as sine, but it starts at at 0, 1.
Yeah, it's just shifted over. Shifted over pi over 2 radians or 90 degrees. So like so. To the right and same deal to the left. And hopefully that'll be enough. Let's make that a little nicer. There. Okay. So secant is 1 over cosine, right? Cosine is 0 when what's true about x?
It's pi over 2.
Yeah. When x is a multiple of pi over 2, right? But this one we don't include 0. 0 is not a multiple of pi over 2. We don't consider that. We want everything to be spaced by pi. So, 0 in the denominator, non-zero at the top. I got my nice vertical asymptotes now. There, there, and there. Now let's finish it off because the cycle to repeat. And exactly the same argument. Just pick it out of the top of the hills. Divide 1 by it. So 1 divided by a positive 1. 1 divided by negative 1 gives you a point for secant right there. There, 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 and there. And I'll let you verify this on your own, but it's going to follow the same pattern as cosecant did. Whenever you start with a hill, hills pop off and upward facing you. So upward facing you, whereas valleys are going to pop off a what?
A downward facing you.
Yes, a downward facing you. So again, this thing is almost exactly like the graph of cosecant, but just what happened?
Just shifted pi over 2 to the left or the right.
Yeah, there was some shifting of some kind. And I'll let you guys compare the graphs to figure out precisely what the shifting amount was. But yeah, notice the asymptotes here are multiples of pi over 2, and they're not including 0. So we had 0 and multiples of pi as our asymptotes last time. But this time we just have multiples of pi over 2. We don't have 0 as an asymptote. Pi over 2, 3 pi over 2. What comes next? 5 pi over 2?
5 pi over 2.
And so on and so on and so forth. That's the graph of secant. Are there any questions about the basic shapes of secant and cosecant?
So secant and cosine will always touch at like whenever the hills are at their vertex, like at 1 and negative 1.
You said secant and cosecant?
Well, secant and cosine, like the green and the black graph will always touch at 1 and negative 1.
Right, because remember, secant is defined to be 1 over the y-coordinates here.
Okay.
The y-coordinates here are the cosine values. And one of the cosine values is negative 1 down here. Another cosine value is positive 1 up here. And 1 divided by negative 1 still stays negative 1. 1 divided by positive 1 stays positive 1. So that's their point of commonality. The 1s and the negative 1s. Cool. All right. Now, guys, let's start to talk about the very last thing with this stuff, which is the shifting and the compression and the stretching with secant and cosecant. But again, these aren't too bad, and I'll illustrate that like so. So here's my graph of cosine and secant, right? Mm-hmm. If I were to change this to, let's say, cosine of, let's say, 2x and secant of 2x, now if I want to preserve this picture here, what change do I have to make to these numbers? Instead of pi over 2, it's going to be what?
Pi over 4?
Yes. If you plug pi over 4 in for there, you get cosine of pi over 2. 2 times pi over 4 is pi over 2. That gives you 0. So pi over 4. This guy becomes...
3 pi over 4?
Yeah. 3 pi over 4. Because again, if you just stick that in there, then 2 times 3 over 4 just regenerates 3 pi over 2.
Okay.
Alright. And Victoria in the corner, 5 pi over 2 becomes 5 pi over
4.
Yeah, it's going to follow that pattern. You got to have that nice even spacing. And now, so yeah, notice that's the graph of cosine of 2x. So secant of 2x is just 1 over that. So 1 divided by these vertical values for cosine still preserves the shape. So for cosine of 2, to graph secant of 2x, all you needed to do was first graph what?
Cosine of 2x.
Cosine of 2x. And of course, draw your asymptotes at the multiples of pi over 4, and just draw them wherever it hits the x-axis. And then again, hills pop off upward facing U's, valleys pop off downward facing U's, and it's the same procedure. And notice that holds if I do even this. Let's say I were to change this. Instead of y equals cosine of 2x, what if I became y equals 3 times cosine of 2x? What's the only change I would have to make to this graph in green?
Instead of 1 and negative 1, it'd be 3 and negative 3.
Yeah. 3 and negative 3, but notice, everything else is exactly the same. So, in order for this graph in black, to be, what is popping off of the hills and what's popping off of the valleys, what's the only thing I need to put in front of secant of 2x?
A 3.
A 3, yeah. In other words, to graph 3 times secant of 2x, all you need to do is just graph 3 cosine of 2x, draw the vertical asymptotes at the x-intercepts, and then start popping off your upward U's from the hills and your downward U's from the valleys. And that's really it. Periods are the same as well. I mean, the period for the graph of this is the same as the period for the graph of this. The cycles aren't as nice. It's abrupt. It goes from a downward U to an upward U, but the repetition amount on the x-axis is the same. All right, we good?
Good. Very good.
All right, last problem. I want you guys to try this. Let's see here. So, have a go at problem B. This is M1B. 3 cosecant times x plus pi. All right, so final challenge. Y equals, what was it, 3 times the secant or cosecant? Cosecant of what?
X plus pi.
X plus pi. So just right off the bat, we can expect some shifting of what kind?
Horizontal shifting.
And look, guys, when you get comfortable with horizontal shifting, you can just skip ahead and just adjust the graph like that. But I want us to do it the other way, which is, again, anytime you're dealing with graphing cosecant of some stuff, secant of some stuff, all you have to do is first graph the well, inverse is not the right word, but graph the complement, the supplement, whatever, of this function, which is 3 times what?
Sine of x plus pi.
Right. Just change the cosecant to a sine. That's 3 times sine of x plus pi. And graphing this is exactly what we did last lesson. Graphing sine and its alterations, graphing cosine and its alterations. So let's go ahead and take this thing piece by piece. What is the graph of, like we were saying, okay, graph of sine looks like this, right?
Yep.
Let's just do one period. Starts at 0, ends at 2 pi. Now, if that's the case, what does the graph of sine of x plus pi look like? Now remember, for these, I want you guys to start getting comfortable with doing it with minus notation. So, sine of x plus pi is the same thing as saying sine of x minus what?
Negative pi.
Minus negative pi. In other words, I just have to adjust my graph by a factor of negative pi horizontally, which basically just means I have to move pi units in what direction?
Left.
Yes. So, here is pi. The pi gets scooted over pi units to the left. At this point, it gets scooted over pi units, so it goes from pi over 2 to the negative pi over 2 mark. So this entire thing just gets shifted back pi units, and we have something that looks like this. I'll draw it here in green. So dot 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 dot. This hill at 3 pi over 2 comes over to pi over 2, like so.
That horizontal line on the green graph will end up hitting the 2 pi, right?
Where?
So
Horizontal line, which one? This
well,
one?
like the dotted line that you have, it will end up hitting the x-axis at
2
2
pi.
pi, right?
Yes. Yes, that's a good catch. So, just a bit more accurate drawing there. So it's going to go like that. So, that there dotted in green is this in black. Like so. Same period, 0 to 2 pi, just shift it over to the left. And final step for graphing this guy, get some more space, is to multiply that by 3. So I want to say y is 3 times all that. That's an example of what kind of transformation?
A vertical stretch.
Yes, vertical stretch with a factor of 3. Now, does vertical stretching affect my period?
No.
No. Same period of 2 pi. So, negative 3, positive 3, and I get this. Nice, slightly more elongated wave. So that's my graph of 3 sine of x minus negative pi, or 3 sine of x plus pi. Now to finish off this problem, what do I have to do?
Well, we're done with 3 sine of x plus pi.
Yes.
So now we just use that graph to graph 3 cosecant of x
Right.
plus pi.
And guys, you may have noticed already, when you're graphing cosecant and secant, you need to draw a little more to your graph. So I don't want to draw just this. I'm going to continue it on a little bit to the left. Let's do one more repetition like so. What do I need to draw at the x-intercepts of the sine graph?
Factors of pi.
Oh yeah, I mean, we can label the graph factors of pi.
You draw vertical asymptotes for cosecant.
Right. Because x-intercepts means the y-coordinate there is 0, and 1 divided by 0 is undefined, which generates our vertical asymptotes. So, vertical asymptotes, and let's do one more. So, I'll do this in green. So the final answer for this is just find your hills, pop off a nice U, going up, values, pop off a nice U, I guess, going down. And just do that. And we are done with the graph. Now, no. Hold your applause for a second. I want us to do one slight thing. Sometimes you'll see problems that have a negative value out front. If the problem were to have asked you to find the graph of -3 times cosecant of x plus pi, say in purple there, what would I have to do with this graph in green?
Have to flip it over the x-axis.
Right. So we'd have one more step where you're to deal with problems with a negative value up front. You take this thing and you flip it, perfectly reflect it over. So I'm going to do this in I'll do this in a dotted black. You have to flip it over the x-axis. So that thing becomes downward U, upward U, downward U. We've got a vertical asymptotes. Okay, notice we always have 3 and -3 as being our minimum or maximum values for a downward U and an upward U, respectively. So yeah, any questions about that? Now, just one final thing. If the question asks you to find the period, again, what's the period of this cosecant graph? Let's say the one in green here, the original problem.
Still be 2 pi, right?
Right. Remember, period is a full cycle. A full cycle for cosecant and secant is the upward U and the downward U. So that happens over an interval of 2 pi. 0, pi, 2 pi, there's one cycle of down and up. Here's another cycle of down and up corresponding to a distance of 2 pi on the x-axis. And with that that pretty much covered it, I think.
Okay.
Now I will say, I will give a shout out to Mr. James Simpson. He requested a shout out, and I'm not one to disappoint. I try to please. So there you go, James.